Okay, great. So, how are you? I think that's nice. That's nice. Feel very energetic for everyone. So it's good to see everyone here. I think it's pretty early in the morning. I think normally in our university in NYCU, usually we have the class starting from 9. That's already very tough for most of the university or the graduate student. But I'm happy to see you guys here at earlier than the 9. So I hope you had a very nice sleep last night. And first of all, today's welcome to this class. So in this class, we will briefly to introduce 3 parts, which is first one, we will mainly focus on what is a semiconductor. So that's pretty crucial. You know that in the last 5 years, I think definitely the semiconductor has become one of the most hottest technology among all the different domains, and then different engineering. Semiconductors becomes a very crucial technology to keep driving for our next generation electronics and also the application, and for sure the crucial, the necessary enabler for our next generation technology, which is semiconductor. So we have to spend some time to understand what is exactly a semiconductor mean and what's a basic structure. So that will be the first part for this class. And second, we will start to move on for the device, because of not only for basic understanding for the semiconductor, we also need to understand that what is actually the structure, the schematic for our device that we can use for our electronics. And then the last part will be the brief introduction for the fabrication. So we will also talk about that in reality industry, how we actually state by state to make this amazing electronic device. So we will also talk about the fabrication. And to be honest, that normally in the university level, these contents cover from semiconductor device and fabrication. It probably will take like more than 1 semester to have very comprehensive systematic introduction. And usually it's combined with the 2 courses. We have one course called Semiconductor Physics and Device, and we have another one called Semiconductor Fabrication. So it's not easy. Try to let everyone to get a little bit understanding with next 2 hours. We just so I will try my best to try to just use most important concept and then the most important knowledge from all these very 2 important classes. So we will briefly introduce, but in general, the idea is that I hope after this class we will get some inspire for everyone who are more interested in our semiconductor and learn some basic related to the semiconductor device and fabrication, and maybe in the future you can consider this as your future study, no matter for the university or even for the future career path. So I actually just talked to our camp staff to try to understand that everyone's background. I'm happy to know that I think some of you already have some connection with Taiwan, probably due to a family connection, due to some of your family was original from Taiwan or has been still in here, and some of you families that you have relative families that working in Taiwan. But I heard about some of you is probably your first time to be here. I'm happy that you consider to, no matter come back or your first time to visit Taiwan. I think that it's a great opportunity. In this camp, I think it's a great opportunity that you can not only learn about the professionals, but also it's a good opportunity to explore some farms in Taiwan, try to visit some place. That's always the purpose. In my group, I also have some international students. I always encourage them not only try to learn lots of professional, but also it's important to make friends, make Taiwanese friends, and also important to explore some beautiful side of Taiwan. We have many beautiful things, amazing food, amazing nature. So it's definitely welcome. Okay, so my name is Tian-Li, and then I'm currently the faculty in the Institute of Electronics, Department of Electronics, Electrical Engineering, and also I'm affiliated with some of the College of Semiconductor Technology and also the some other departments. So today we will try to give you some brief understanding what is semiconductor and why we have to study, and then what actually the history, and then some outlook in the future. So the first one, why should we learn about semiconductor? I think, as you know, that you all guys have very advanced electronics on your hand. You use the iPhone, iPad, the MacBook, or other laptop every day, even some of the very fancy AR, VR application. So in general, all these iPhone, iPad, laptop, and also the computer actually all rely on the semiconductor chip. And then we can consider this chip as a kind of like a brains that actually help us to do the computing, control, and data transmission. That's a basic function for this electronics, for this computer chip, because of we need this computer chip because, you know, the human brain is very awesome, but sometimes we do hope that our electronics can be processed, can digest information, process information, transmission information even faster than what we can do, and that would be highly helpful for our life. That will highly benefit for the future society. And then the key part for this electronics is a computer semiconductor chip, which is generally like the brain of this electronics. So that's why we have to learn about the semiconductor. So here is just some examples that in some of the application electronics that you use every day, that what's actually the details of this electronics inside. So this is an Apple A17 chip, and then that's the world's first smartphone chip built with 3 nanometer technology. So the nanometer is a very important unit for semiconductor people like us. So in general, nanometer is referred to the ultra small length. That usually means that actually it's a really small scale. So how small the nanometer is? So just give you some ideas. Usually we will refer to the meter, and then in our daily life we very often to use a meter and centimeter. So centimeter, which is equal to 10 to minus 3 meter. And now we have the further downscale, but that will not often see in our daily life. Now it's more in the engineering science study. We will talk about the micrometer, which is equal to 10 to minus 6 meter. And now further beyond the micrometer, if you talk to the semiconductor people like 20 years ago, we all talk about in the range of a micrometer. But as you know that for semiconductor people, what we try to do is try to make our chip smaller and smaller. Therefore, the micrometer still considered as big for us. So the next stage, we want to have the chip in the range of the nanometer, which is equal to 10 to minus 9 meter. So this is just some of the key numbers that we will use very often when we try to measure the scale of the semiconductor, which is just normally in the nanometer. And then the idea is that if we can try to make our semiconductor smaller, that means that we will have the more components per chip. So that means inside our circuit, we have more components in the one chip. And the more components also suggests that it's faster speed, better performance, and a lower power use. So that's the basic idea that why we have to keep working to push our semiconductor technology become smaller and smaller, because we want to have the inside the one particular fixed scale, for example, fixed space, just like in this classroom. We want to use the same classroom, but we want to put more and more people in this classroom. And what should we do? So we just have to make each person as smaller as possible. So in the end, the result of leading this scaling down will lead to the faster speed, better performance, and also the lower power consumption. Because imagine that if we try to put 100 people in this classroom, ideally we will consume 100 times more water, more bottled water, more food that we need to supply for this the people inside. But this is not exactly what we want, because we want our chip have more semiconductor component inside, but in the end, they will consume less power, because otherwise you won't have the smartphone that can last for the 12 hours. So I think right now in the most of the advanced smartphone that you only charge once per day, you only charge during the sleep, but you can use whole days. But if you back to the 10 years ago, when I was 20 years ago, when I was a student, I'm not that old, so it's just that 10 years ago when I was a student, that actually we have to charge our phone 3 times per day, because our chip is not that save the energy. It's pretty like a power consumption. So in the end, is that we want to have a high performance chip, more chip, faster chip, but we also want to have less power consumption. So this A17 is a chip is built by the TSMC, and now has a 19 billion transistor inside this tiny chip. And therefore, you can imagine that this is an amazing engineering miracles here. It's how we can try to pack so many chips inside this really small dimensions of this. In general, that if you look at the history of the semiconductor, now it's more than 60 years, 70 years development, but it's right now we can consider as engineering miracles. There's one particular terms we have started to mention here. It's a transistor. So the transistor is a term we try to describe the main device inside the semiconductor. So in the future, you will hear very often that the term related to transistor, because transistor is a kind of a very important component in the end to help to control our whole entire electronics. So that's what we call as a transistor. So semiconductor in general can be considered as one material, but we use this material to build out a transistor. And once we have a transistor, we use this transistor to control our circuit, control our system. That's how we have so far. So transistor is a very key term that we will use over and over again. You will hear, for sure this is first time, but at the end of this class, you probably will hear about more than 20 times the term related to the transistor. Okay, so that's one example. And another example shown me here. Most of us will put a lot of focus on our smartphone, because we feel like we are pretty like fortunate to have this very advanced smartphone to help us to do a lot of things every day. But sometimes we forget that this smartphone needs electricity. And how we can transmit the electricity, you know that we have the different power planet. And then the power planets are built out in the far away region, and originally they generate a huge of power. But how do this electricity in the end to transmit to our electronics device? Then we need this what we call the charger. How we call the charger here. So the charger is also another electronics that the component, that the application you need every day. You can have a very good smartphone, but you definitely cannot have the charger, because otherwise your smartphone will be just like that. You cannot use anymore. So actually inside this charger, there are still so many semiconductor innovations inside. So this is a typical schematic for the iPad charger. And then if you try to look at this one, this is some of the tear down schematic to review that there are many components. There are many components, powered by this semiconductor technology. That's give us the most important, safe and also efficient charging. So imagine that when we always talk about the electricity, what we hope is that we can charge our electronic device as fast as possible, right? You won't want the charger that you have to wait for the 5 hours finally to make sure that your cell phone is a full battery. So we always hope that we can charge less than 1 hour, probably less 30 minutes. In the last 5 years, we start getting more and more innovation of this charging system. For example, now in the market, you can easily to get this kind of like a gallium nitride charger. So they claim that they can charge your device probably in the 10 minutes up to the 50% of the battery. And this charger is not also can charge faster, but also can be charged for the multiple device. I think all these already on the market now. You can easily have that. You have one charger, you can charge for the 5 electronics. That's all set to this very amazing semiconductor technology here. So this is a typical circuit diagram inside these chargers. And then this is our typical what we call the circuit diagram. And I'm not sure that because you guys' background has a little bit, first of all, you guys are a little bit far away from my age. So I actually don't know that what you guys have been learned in the past. I heard about some of you. Probably is high school, senior high, junior high, probably. So anyhow, I'm not sure that what's your actually the basic understanding of our semiconductor technology. So I just assume that you probably the first time. So therefore, this is what we usually talk about the circuit diagram. So the circuit diagram, inside the circuit diagram, we can see that there are many important semiconductor components. For example, this one. This is the one that's a typical we call the MOSFET, which we will talk about this later. So the MOSFET is the most important transistor that we use nowadays. So then you can see that inside this circuit, we already see that some of the semiconductor component. The first one, later we will introduce the MOSFET. Actually, the T here is an abbreviation of the transistor. So that's why now you can see the transistor is a term that we will use again. But it's a very special transistor that we call the MOSFET. And then, in addition to MOSFET, we will see that there is this one. These symbols means the diode. And then diode, which is a semiconductor device that combines the 2 different kinds of semiconductor material, which particularly we consider the P-type semiconductor on top of our N-type semiconductor. So which is a kind of structure that we put the 2 different semiconductor material together, and in the end become as one kind of the device that we call the diode. And we will also talk about the diode, the basic operation, and then what would be the diodes look like later. And also, in addition to this component, diode, MOSFET, there are also some of the components that we generally call as the passive component are very important. For example, this one. This is what we call the inductance. And this one, this is what we call the capacitance. So, and some of these still we need the resistance, but it didn't have the resistance in here. But in general, not only the device, we also need some basic component like the inductance, like the capacitance, like the resistance. So that's how we actually use to build up our whole electronic circuits. Okay, so the next is that before we move to the further discuss for semiconductor, I think definitely it's worth to let you know that the very critical laws that the industry try to follow, try to catch up, is what we call the Moore's law. So the Moore's law, what does mean the Moore's law? The Moore's law actually means that the number of a transistor on a computer chip roughly doubles every 2 years. So that's actually what does mean. That actually means from the Moore's law. So the key message here is that the number of a transistor should be double every 2 years. So this means that the more powerful the chips inside the one specific space, which means that our computer and smartphone can run faster and can do more things here. So that's actually the some of the implication coming from the Moore's law. As we have already said that our goal is want to pack more chips inside one particular area. That's how we call it density. So we want to have the density increase. So if we can follow the Moore's law that every 2 years and the number of the transistor can be double every 2 years, that means our density can keep increasing. And if our density keep increasing, that means that our semiconductor chip can become more and more powerful, more faster. And this law was proposed by the Dr. Gordon Moore, which is a founder of the Int'l. And then he proposed this in the 1965. And then interesting to know that this law is not actually it's not developed by any very rigorous calculation or lots of, it's not developed by any very detailed physics. Actually, it's developed by his pure observation investigation at that moment based on his experience. So he proposed this Moore's law. It's based on, it's purely like the empirical law. Just follow his observation, his experience. But everyone will be very surprised that after so many years in nowadays, we really can catch up this Moore's law, and then this Moore's law become the golden rule for the semiconductor industry, because of these laws help us to understand why technology has advanced so rapidly in the nowadays. Just for example, in the past, we have one computer that usually takes up the whole entire room. So we have this kind of room, but this kind of room can only allow one computer. But nowadays, thanks for the push coming from the Moore's law, all of the semiconductor company, all the semiconductor engineering works hard day and night, try to make sure that our next generation technology can follow the Moore's law. And now we have the smartphone that has 100 times of a more powerful than those early machine, and then also is packed into smaller and smaller chips. So that's all thanks to the push coming from the Moore's law that make the actually impossible become the possible. So this gentleman actually we can consider as a very senior gentleman. Actually, he was already died just probably like 2 or 3 years ago, and he's almost in the very senior age. So actually, it's a very senior legend in the whole semiconductor history. And then he proposed this one, and then you can see that this is a graph that compare with the Moore's law versus the real transistor count here. So these blue dots are the real transistor count, and then this black line are the prediction, the investigation coming from the Moore's law. So we can see that the Moore's law has accurately predicted the path of the technological advancement over the past 50 years. And then we hope in the future we can still keep the same pace like the Moore's law. That means that we will have more and more very incredible semiconductor chips that can produced for the benefit for this society, benefit for the human in the daily human life. So that's why the Moore's law. If you look at the semiconductor news, everyone's talking about whether the Moore's law is dead or not. It's always a argument since from last 10 years. And then I think for all of the semiconductor engineering, the goal is that we need to propose more innovations, no matter coming from materials, device, system level, and to make sure that we can follow the Moore's law. That's become the golden rule for the whole semiconductor industry. So here, let's look at the industry analysis. So in the last slide, it's mainly like some of the prediction, observation coming from the Dr. Gordon Moore. But let's look at the real product, where our real product can make it to follow the Moore's law or not. So this is a talk coming from the previous chairman, Mark Liu from TSMC in the 2021. Of course, in the last several years, the TSMC keep updating the new industry roadmap. So this is an industry roadmap. So now you can see that usually the roadmap is indicate as a kind of the technology evolution from past and then to the future. So you can see that we even consider as a Moore's law as our roadmap. We try to make our product, our very novel product, lots of innovation to make sure we can catch up this Moore's law, this roadmap. So how do we actually, what is actually happening in the last several decades? What kind of the technology advancement that leads to us? The technological advancement improve chip performance. So as already said that our goal is the chip performance roughly double every 2 years, which is kind of the Moore's law. And then in this one, we can see this is a red dot. It's a real product, figure of merit. And then this white line is basically as a Moore's law. So we can see since 2005 until now, 2025, actually we are doing very good job in the last several decades, try to squeeze our brain, make a lot of innovations to try to make sure our technology can follow the Moore's law. And the next one is some more details that how we can make it. So actually there are the two main directions that in the past that how we can make it to follow the Moore's law. The first one is what we call the equilibrium scaling, which is this one. From the 2005, roughly up to the 2012, 2013, that we have the equilibrium scaling. So that means that we actually want to shrink transistor and pack them more and more densely inside the chip. So if you talk about the original idea, as I already said, that our goal is we want to make this room, we have more and more workers, more and more engineering in this room. So the first ideas come to our minds definitely that if we can make our engineer, our worker, ideally making them smaller and smaller, of course, then we can pack more people in this room. So that's also the same idea that come in early time, that how we can make it to make our chip advanced. So we call this as equilibrium scaling. We try to scale, we try to shrink our transistor in all different dimensions. There's some technical terms. There's a length, there's a width, there's the geometry, there's a thickness. Anyhow, we just shrink in every dimension and try to make it as smaller and smaller. That's what we call as equilibrium scaling. And there's some innovation here that we won't talk too much, just let you know that there's some technology already has been studied. For example, the strength silicon, we use the silicon as a main material for semiconductor, but we do some magic. We try to put them as an additional mechanical stress, then we call as a strength silicon. And also we have another one called the high K metal gate. So these two are the two main novelty allow us to do the first step to keep following our Moore's law. So that's happening between 2005 and 12. And then, of course, each one, you probably, actually each technology for the strand silicon, for high-K metal gate, from the research in the lab till the product that we use, it takes like 10 years for study. We have the ideas come out with in the lab and then do some prototype and then move on for the manufacturing. After manufacturing, we also need to make sure that we reach the yield quality. We want to have a good yield. So it always takes time, more than 10 years for this development. But at that moment, we mainly use these two. And afterwards, we found out that's not enough. We need something new, novelty. We need something new, innovation. So therefore, we start to consider the new transistor structure and materials here. So transistor structure, the first and the most important one is what we call the FinFET. So you can imagine that the film, probably when you talk about film, this kind of words coming from the fish film. So it's mainly the term that we borrow from the fish. So actually it's a 3D fin-like structure. So we make a certain geometry device as a little bit 3D dimension like the fish fin. So that's why we call it FinFET. So that's one of the very important innovations. And also later we have this what we call the EUV lithography. So basically we have this very, very advanced lithography that we can try to make our line, our electronic line, our electronic interconnection line as smaller as possible. That's what we call the EUV here. And also we have some additional what we call the high mobility channel, and also what we call the design technology called optimization. So these are the lots of innovation happening in the last 10 years to help us to allow us to have the great fortune to enjoy our technology so far. And each one, as I say, takes more than 10 years. But this shows that in the semiconductor world, you will never feel boring because you always face a new challenge. You always enjoy the new innovation. You will keep yourself in the very advanced knowledge in front of all human because of this semiconductor technology is a technology that will need lots of the novelty to keep evolutions. Okay, so that's happening in the history. But for the future outlook as a prediction analysis coming from TSMC, you can see that expected by the 2030, we probably have more than 1 trillion transistors inside the one chip. That's a goal. So, and then there are many getting more and more innovation here. I won't go very detailed because that's very hard. That's even for graduate student cannot really follow. But just let you know that there are so many novelty and innovation and so many science and so many engineers. Very smart science, smart engineering, smart chemistry, smart physics come to join this field that in the end make us to reach for possibly 1 trillion transistor by 2030. So you can imagine the chip as just like as a factory, and then each transistor is like the worker. So our goal is want to pack more workers into a small space, and also make them work faster, more efficient, and less power consumption. So that's actually the goal. So in general, why we have to make our transistor from the micrometer to the nanometer, even further, why we have to keep increasing the density, that's actually the goal, just like as mentioned here. So I hope this one can get you a rough understanding that the bottom up motivation for us to drive for this semiconductor technology. Okay, and let's look at some of the detail of related to this nanometer level chip. So this is the TSMC publication about their 5 nanometer semiconductor chip. And then this is the paper published in the, we have this kind of the very important electronics device conference happening every year. It's considered a semiconductor Olympic kind of the competition and exhibition that we call the IDN. The full name is International Electronic Device Meeting. So every year in this conference, all the very advanced development in semiconductor we can see in this conference, and also lots of companies will showcase their advanced breakthrough. So this is one of the paper coming from TSMC in the IDM, and then you can see that regardless of the details inside, we won't talk in detail inside. Just show that if you look at the title of this paper, this is a 5 nanometer. So I think the title is very straightforward. Yeah, they make it for 5 nanometer with a certain CMOS production technology, and also they talk about EUV, which we also have been mentioned in last slide, and high mobility channel FinFET. So again, this is some term that we have been talking about. So now you can see that the slide we talked about in last slide actually is just exactly the product that we use in our day, and then it has been already reported in the last couple of years in a very high level conference. So we don't understand if you don't understand the detail of this paper, it's fine, but at least you got to roughly understand that this is paper talk about 5 nanometer. They use EUV, they use FinFET and make it. So we have been explained the nanometer is extremely small unit of length. A smaller transistor allows chip to have more function, faster speed, low power consumption. And some key features for this TSMC 5 nanometer technology, including the EUV. So enable the finer and more precise circuit patterns like the drawing with an ultra-fine pen. So that's the idea is why we need to use the EUV. And also they use a high mobility FinFET here, so that allow electrons to move faster, boosting performance and reduce power consumption. And also the ultra density SRAM. SRAM is kind of a memory, and it's good to showcase that each technology can improve their SRAM density. So in this case, they achieve the density in such scale. So in this paper, they also show the difference between the compare with the 7 nanometer. So what they show is that they reach around 1.84 density improvement and 50% faster, but the most important, 30% lower power consumption, because we don't want that our chip become faster, become powerful, but the power consumption increase, because otherwise we have to charge our device very, very often. This is not exactly what we want. So in the end, we still hope our chip can be very efficient, can have less power consumption. Okay, so of course there are some more technology demands that driving chips to our become more powerful. In the end, it's always our technology demands based on our human needs. That's how we hope. We hope to have the electrical vehicle car. We hope to have this artificial intelligence. We hope to have this robot. We hope to have this faster communication. So this 5G communication, artificial intelligence, cloud computing, electrical vehicles, these all innovation application that all drive the chips has to be developed in the more powerful, more faster, because we need this chip to make this application happen. So that's why you can imagine that the semiconductor can be the technology that they never will ending, because of as a human, we always want to have the more advanced technology to benefit our life. And once we have a very advanced technology, in the bottom, we always need a very advanced semiconductor to make this technology possible. Okay, so then we still need to look back some of the history. This is a little bit old picture, but it's very historical picture because this is the historical moment when human first to make the circuit smaller inside the one kind of like a metal, one place that's actually is developed by the Jack Kelby in the 1958 at the Texas Instrument. So this is the first integrated circuit developed by the Jack Kelby in the 1958 at the Texas Instrument. So this is the first time to have a complete chip was built on a single chip. So that's how we call as a IC, integrated circuit. Integrated circuit is a very important term. If you are interested in semiconductor, you have to know about the IC. You have to know about transistor, you have to know about the FinFET, you have to know about EUV, you also have to know about the IC. So before the IC, circuit was hand wire using separate paths, transistor, resistor, and then Jack Kelby's breakthroughs combine all components on the one material. And this integrated circuit is that's how we call this is an integrated circuit. So the simple idea is that we put a full circuit inside a tiny chip. So that's the important demonstration. Although this circuit doesn't look like very fancy, but there's a lot of the inspirations after this demonstration. So that's why we have these very beautiful, amazing engineering miracles at this moment. Okay, so also because we start to look at some of the great historical moments, so it's good to also understand that the evolution of our microelectronics from early time till now. So in the early time, we have what we call the vacuum tubes. So vacuum tube is used in the early TV, radio, and radar system. Probably if you ask your parents or grandparents, they still have a memory. At least when I was a young kid, that we still use TV inside as a vacuum tube. So in the end, the TV is quite large because of the vacuum tube is pretty bulky and we need a lot of space. So that's actually not the goal we want, because we want to try to make us everything smaller. So afterwards, we start to have this what we call the bipolar transistor here. So this start beginning of the modern semiconductor technology that we have. This is the first transistor we developed that we call the bipolar transistor. But the bipolar transistor has some advantage, but also with some disadvantage. So we want to have the chip that can has less power consumption, has a faster switching. So that's why since 1960 we start to have the MOSFET, and this has a very good, very attractive feature that have the extremely small, faster, and energy efficient. And most important, the MOSFET becomes the foundation for the all computer and the smartphone chips here. And then we now have the tens of billions of the MOSFET on a single chip today. But just want to say that it doesn't mean that we don't use the bipolar transistor anymore. We still use it for certain application. We still needed the bipolar transistor, but now it's kind of like a majority we use the MOSFET. And among the very specific application, we still need the bipolar transistor. So, and then if we look at what actually the secrets in the past, try to make our transistor faster and then the energy efficient, and actually we have the two directions that we have already talked about briefly, and then now we talk again. So this is the first one. We have this we have the materials innovation. So the material innovation, the goal is we want to make our transistor faster. The faster transistor, just like we try to boost the speed. So you just imagine that you are in the microelectronics, in the semiconductor world, what we actually consider the main carriers inside we consider is electrons. So we just hope our electron inside this semiconductor can be faster, just like when you drive the car, you want to drive faster. So we want to make it certain way that our electron can be faster. So there are several innovations where we have been mentioned. Strand silicon, germanium channel, 3-5 material. So we won't talk too much in detail, but just let you know. And then the ion here is actually means the I here is actually means the current. So the faster transistor, so we want to have the higher current. And then also, after we have the materials innovation, then we start to have the structure innovation. And then for the structure innovation, the goal is to enhance the control, better control with ion over ion. That's we usually call as the on-off current ratio. So we have on current over off current. So this ratio becomes another important figure of merit because of the off current here actually is pretty important related to the power consumption. So if we want to make our chip can save the energy, less power consumption, what we need to make sure is that it must be off current. And what means off current? When you right now you guys are very concentrated on the class, so your cell phone is off. But in the idle of our electronics, ideally it still will have some currents pass by, although it's not turned on, it's in the off state. But this off state will still have some off currents inside your chip. So now if you don't use your cell phone, but if your off current is high, that means that your device, your smartphone, your battery will die very soon because it still consumes lots of energy there. So that's why we want to have the low off current, because that means that our electronic device at the off state can also save the energy. So this innovation makes your smartphone not only faster, but also more durable. And also it's important, cooler, because of this current also in the end is related to the thermal. If you want to reduce this thermal issue, then you have to make the off current become smaller as well. So that's the ideas behind. For that's why we have to have the different innovation. So we have what we call the silicon on insulator. This is a transistor mainly on the insulator. And then we have the FinFET, and then also the ultimate goal, we have the network wide, that's we call the very advanced transistor. So if we talk about the FinFET, then we have to definitely to mention who is the father of FinFET, and then we have to talk about the Professor Chen Hu. So Professor Chen Hu, now he is a professor in the UC Berkeley, but also is a chair professor in our NYCU, and he is known as the father of FinFET, and for his pioneer work in this advanced transistor. So what is FinFET here? So as I say that this is because of his innovation, he's dedicated in the FinFET in the end, from the lab to the fab to the production. That's why that he got some awards from the President Obama to thanks for his dedicated efforts in the FinFET. And actually fin, what does FinFET mean? So fin is a kind of race-like structure. It's a race structure shaped like the fish fin. So the left-hand side is typical transistor. This is the device structure. We call the MOSFET. We will talk about MOSFET later, just let you know that what actually the MOSFET look like. And then the right-hand side is what we call the FinFET. So you know, and you can see, simply compared to these two figures, the main difference, you can find out that the FinFET has a vertical structure of a gate, right? So this region is vertically, not like this one. So that's why the FinFET is a raised structure shaped like a fish fin is mentioned about this part. So that's why we call as a FinFET. And then the FET, the original FET is what we call the field effective transistor. It's a basic blocking for the modern chips here. So why is FinFET important? So traditional flat transistor lose the control of when they shrink. When we try to make us a smaller and smaller, just some brief basic operation, just to let you know that normally in this MOSFET, what we typically do, later we'll talk detail, but what we usually do is we will bias here as a gate bias, and we'll bias here as a drain bias. And once our gate bias is larger enough, you know that the positive bias will always attract some electrons. So then you will have some electrons here. And this is a region where we call the channel. Right, so that's I think this is a pretty like a high school physics that the positive bias will always attract electrons. So at a certain moment, you will accumulate enough electrons on this region. And then because of our drain bias is a positive, so the positive means that the electron will try to flow from left to the right and become the current here. And here I use the position of the electrons because the electron is attracted by the positive bias. So why we call this is flat? Because of this channel is flat. So that's why we call this as a flat. But the problem is that if we do the shrink, we make this smaller and smaller, we got a problem that that's why we concern for leakage current. So I won't talk too much why there's a leak current, but just let you know that there's a critical concern about the leakage. So that's why we want to have a better control of this leakage current. So that's why we make as a transistor in the 3D dimension that the gate is wrapped all around the channel with 3 sides. So we have a channel here. You have to a little bit come up with some imagination. We have a channel here. Not only the top side, but also the 2 side walls. So we have the gate that wrap the channel on the 3 sides, and this gives us a better, strong control and better performance. So in a FinFET structure, the gap wraps around the channel on 3 sides, provide a stronger control that gives us a faster, stable, and more power efficient. And so the FinFET is like just, you can imagine that actually the transistor semiconductor device is like the faucet. So the FinFET is like a 3D version of the faucet. So then you can allow the better control of your water flow. So then once you turn on, once you turn off, then you turn off, you can completely then make sure that the faucet is off, there's no water flow. But if you turn on, you can make sure that the water can flow so fast, and then the amount of water can be so big. So that's the idea for this FinFET. So this is a very critical technology to enable for the advanced applications. Okay, so now finally we give a pretty like a short overview of what is the technology. So we have to move some of the more basic fundamental foundation part, which is what is a semiconductor. So semiconductor is actually, I think everyone's here. We have, I think for this camp that we have the 4 different groups, and 3 groups is mainly provide for local student, and only 1 group is provide for the international student like you guys. For you guys, I think in English is not a problem for you, so you can probably already can guess that the semiconductor from the name, it already have the implication. It's a kind of a conductor, but with a semi kind of characteristic. As you know, the semi means that you have the partial. So actually the semiconductor just a conductor that has a partial conductivity. So a material that is partially have the conductivity. That's what we call the semiconductor. If we look at the two completely case, one is what we call the conductor. So conductor is mainly like a metal. The electron can easily flow in the metal. We don't have to give any particular condition. They can very freely flow in the conductor. And on the opposite side, we have the insulator. So insulator, that means that the ideal insulator, we should not have any current. We should not have any electrons inside this material. And the semiconductor, just materials in between. We can control the conductivities by using additional bias to modulate the conduction of electrons between the conductor or the insulator. So semiconductor is a material between the conductor and insulator, and the most important is the semiconductor has a partial conductivity, and then this conductivity will change when we consider the temperature or voltage. And then why the semiconductor are so powerful is because of semiconductor that can be easily controlled, because so we can switch the materials characteristic by applying the additional bias. So imagine then this material can be the material that we can use as an electrical switch. So for normally, if you look at the turn on, turn off light for turn on, turn off switch for the light, that's what we call as a mechanical switch. Just somewhere here, it's usually we click and then our light turn on, we click twice and then our light is off. But the inside of this is a mechanical switch. It just has a certain connection of a metal wire, and then once the metal line connected, then the light is on. But the problem for mechanical switch is that it's switched too slow. So we want to have the technology can switch very fast. So that's why the electronic switch, the electrical switch is important. This electrical switch will become the foundation for transistor and the modern electronics here. Because of electrical switch, that means that we can give the bias and then it turn on, and we can immediately stop the bias and then it turn off. So we can control this on-off by any condition we like. And then also it's important that it can work very fast. It's faster than any other switch can make it. So there's a several kind of the thoughts you think about the semiconductor. So the conductors might be considered as a faucet that's always open, insulator that's a faucet that's completely off, and then the semiconductor is a faucet that you can control anytime based on what you need. So also we can consider semiconductor is kind of like the door. So when a certain condition, for example, voltage reach a certain threshold criteria, then the doors open, the electron can pass through, and in the end that causes electrical currents. So once we understand the basic purpose for the semiconductor, then the next is that which kind of material we can use for the semiconductor. So then we have to look at the chemistry species in the periodic table, and inside this periodic table, normally the most often used species that can be used for semiconductor is coming from the group 4, group 3, and group 5. Of course, there are still some other elements can be used for semiconductor, but the majority, I would say like more than 80%, we will consider to use group 3, 4, 5, this element for the semiconductor. And we have a different type. And the first type is what we call for example, silicon germanium. So where is the silicon? So silicon is in group 4 here. Silicon is here. This is silicon. And this is, this silicon, and this is germanium. So this is group 4. And then the silicon, the main advantage for silicon technologies can provide us a low power consumption. So that's for the good for the energy saving. And then I would say that 80% of our electronics are mainly built up by the silicon. Silicon has been discovered for very good material for semiconductor since more than several decades. But I believe in the now and the future, silicon will still be the main dominant material. But for the other application, silicon cannot make it because of due to material property. Silicon sometimes still a little bit slow and sometimes cannot sustain the high voltage. So that's why we will still explore some other material. So therefore, we have a second type, for example, gallium arsenide or indium phosphide. So which is a material in the group 3 and group 4. Group 5 is a combination. So this is Ga, this is As. And also we have this is iron, this is P. So we make the combination of group 3 and group 5 and become the one kind of the semiconductor here. And for this two, it's good for the ultra high speed, for the faster communication. And also the last one, we can also consider as the different combination for this group 3 and group 5. So we have the Ga here, but then we put the nitrogen, or we have the silicon combined with carbon. That's what we call the silicon carbide. And this kind of semiconductor material also good for high speed, high voltage, high temperature, high power. So that's why it's very good for application like the charging or like extreme environment. And the extreme environment here, what I mean is sometimes it's not in the Earth, it's out of Earth. For example, if you talk to the NASA people, what kind of the semiconductor they want to use for their sports exploration, for their spaceship, they will consider the gallium nitride and silicon carbide because these materials are pretty stable. So that's for the extreme environment. So then in this case, we can divide the semiconductor into two different categories. One is what we call the element semiconductor. This is only the material that combines with one single element. We have what we call the compound semiconductor. We have the multiple elements here. So we have been already say silicon is most common. This is most important one, most common, used nearly all the consumer electronics. And then we have several compound here. So we have these two that's used for optical communication, radar, and these two can be used for EV, fast charging, or 5G here. So basically, we can have lots of the freedoms here, try to combine the several different material and become one particular semiconductor material that fit our needs. And also, when we talk about the semiconductor material, there are four critical properties. First is conductivity and band gap and electron mobility, and also the thermal stability. So these are very important for our semiconductor materials. So what is a silicon crystal structure? So you can imagine this is like trying to stick the different building blocks together, and then in the end they will arrange as a 3D cube-like lattice. That's what we call the cubic crystal, and each silicon atom has 4 neighbors that were bonding together, and that's what we call the covalent bond. And covalent bond is very strong and stable atomic networks here. So this is a 2-dimensional top view. That's for the silicon atom arrangement, and this is a 3D dimension for this cubic silicon lattice here. So that's just for your reference what is actually the silicon crystal look like. And when we talk about this silicon crystal, and then the next phase is we need to understand why the silicon or why semiconductor can be conductive. The reason inside is because we have electron and holes inside this material that in the end will become the conductions. So the covalent bond, just like you have the silicon atom that will be holding hands together, and then in silicon crystal, each atom will share the 4 electron with the neighbors as shown here. So each silicon we have the 4. If you look at this silicon, we have a 1, 2, 3, 4, and then in the nearby silicon we have another 1, 2, 3, 1, 2, 3, 4, and then because of these two will be bonding together, that's what we call the covalent bonds here. And then, what happens is if there's an electron breaks and become freeze here, so the electron might gain some energy and start to escape from this bonding here. And once it escape from the bonding, and they will become the free or conduction electrons, which is this one. So then this becomes the conduction electrons, and then you will contribute to our current here. And also there's another opposite concept that we call the holes here. So the hole is just considered as an empty spot that's left behind. So once you have this electron move here, then this will become empty. And this once become empty, and then that will call as a hole here. So this is some, so like the empty seats, the other electron fill in, so the holes appear to move. So you have the one empty place like move with each other, that's we call as a holes. And then the most magic thing for semiconductors is we can actually do something to change their conductivity. We can try to dope some additional atoms. In the end, their conduction will change. So that's we call the doping. So the doping means that by adding a few dopant atoms, we can greatly enhance the material's electrical property, especially the conductivities here. So we have two types of the doping. One we call the donor, one we call the acceptor. So donor just like an electron giver. So if you imagine that in the one silicon material, silicon is group 4, and then you put a one group 5 species, for example, the arsenic. So arsenic has 5 electrons, right? So that means this one, additional one here, will start to become as a free electrons. Because the arsenic has 5 electrons in the outer shell. So then this additional one will become free electrons here. And now we have this material is getting more and more negative electrons. So that's we call as an N-type semiconductor. And N here means the negative. And similarly, we have another one called the acceptor. And we can consider this is what we call the hole creators here. And we just added the group 3 like a boron. So in the case of a group 3 like boron here, so boron only has 3 electrons in their outer shell. So that means boron will create the one empty seat here. And this one empty seat will allow another electron to flow in here. So this group 3 will create the hole, which is the missing electrons in the second bond. And because of the holes can be considered as a positive charge here, then we call as a p-type semiconductor. So in a nutshell, that once we have the donor, more and more donor, our semiconductor become N-type. And once we have the acceptor, and we put the group 3, and then our semiconductor becomes p-type. So now we can start to manipulate this semiconductor material by adding additional atoms. So that's a very cool thing that there's no other material can make like in this way. So in a summary, when we consider the p-type and N-type semiconductor, so p-type is mainly based on group 3, N-type based on group 5, and then p-type is due to the holes, and this N-type is due to the electrons here. So that's a main summary for this N-type and p-type semiconductor. And the next one is that normally when we start to have to understand the semiconductor device operation, first we need to spend a little bit of time to talk about the quantum physics. I'm not sure that any of you have already heard about the quantum physics, but you must already know about the Newton physics, Newton mechanics. So then we have to make the comparison that what's the difference between the Newton physics and Newton mechanics and the quantum physics, quantum mechanics. because of in the micro world, if we down to very scale, actually the scenes actually become a little bit different than what we expect in our daily life. Imagine that if you are the skier, so once you miss some obstacles here, you will. The only things that you will try to avoid this obstacle is that you might be jump, or either you will crash onto this. That's based on the typical Newton mechanics here. But in the consider as an electron, actually, when the electron miss some of the additional barriers, actually they won't jump, they won't crash. Actually, there's a third scenario. That's they call the tunneling. So that means that imagine that the typical Newton mechanics tell us that if you have the walls here, if you have a certain wall here, and the Newton mechanics tell us that you throw the ball against this wall, there will be the only one scenario happen is you will see the rebound of this ball, right? That's happened in the every daily life. So that's based on the Newtons. But in the case with a quantum, then that's a different story. In the case of a quantum, still imagine the electrons try to move across this wall, and normally we call as a barrier. Of course, we still have certain reflection, but there's also the chance this electron will tunnel through this barrier and reach to the other side. So that's a main difference between the Newton mechanics and quantum physics. Because if we keep using the Newton physics, we won't be able to explain everything we found in the semiconductor world, in the micro world. That's why we have to introduce this quantum physics here. So you can imagine that the electron is like the mass runner. The atom in the crystal form is a periodical array of these different atoms here, and then the electron move like the tiny ball in this mass, which will actually influence by this as well. So then all these electrons actually will try to move, and then although you know that each atom has a different the very physics term, how should we call the potential? So the potential ideally will influence this small carrier move, but the electron will still try to find a way to move across this potential, which is a barrier, which is a wall. So, but at this point, the Newton's equation is no longer valid at this moment. So that's why that we need to start to use quantum mechanics and use a concept like a wave of probability, because of that's how we deal with in the quantum mechanics. We consider as a wave, we consider as a probability. So in summary, in the case with consider very small things like the electrons, so it doesn't necessary to follow the straight path, and then we need the quantum mechanics here. And also the most important is that we might have this quantum tunneling, and this is exactly the thing that our conventional Newton mechanics cannot help us. That's why that we have to learn the quantum physics. Of course, the quantum physics, quantum mechanics is a very complicated knowledge that usually in the university level, we probably will spend 1 semester, 2 semesters to talk about the quantum mechanics. But the good thing for semiconductor, we are the engineer, we are not the pretty like fundamental researcher. We are just trying to apply this quantum to in our practical case. So that's all. We don't have to spend the 1 semester to understand quantum physics. Actually, in my class, just 2 hours, we just talk about quantum physics in 2 hours, and in the conclusion, just try to let you know that the quantum, in the quantum world, in the micro world, the electron can tunnel through. And then the knowledge for this, that's enough. And also another important difference between the classical quantum mechanics is that the classical mechanics that we can know exactly where the particle is. For example, if you try to play the basketball, you know how fast the basketball can move and what is exactly the location of this the baseball will drop here. So we can apply the classical mechanics so you can predict the position very accurately. But when we talk about quantum mechanics, actually everything is become impossible to predict precisely. So therefore, we need to start to have the concept of the probability. So just like in the case, if you try to use quantum mechanics to find the kitten, you probably know where this kitten can be under the sofa, in the kitchen, but you cannot just precisely determine the kitten. So the only way in the quantum mechanics is that in the end, we have to apply the concept of the probability. So that means when we talk about the behavior of the electrons here, we cannot precisely to know where our electrons. We can only know 50% electron will be in the place A, 30% in the place B, 10% in the place C, and probably 5% just in the place D. So everything is in the case with the probability. That's the main information that we want to deliver for the coming from the quantum mechanics that in the end apply to our semiconductor. Okay, so the next one is that we will talk about the band gap. In the semiconductor material, there's a very important material property that we call the band gap. So we have the term what we call the valence band here. And then we can imagine that this is like the valence band is the place where the electrons stay and forming the covalent bonds. And then just like the well-behaved students sitting in their seat in their chairs. And then we have another what we call the conduction bands here. So once the electrons gain some energy, so here is a valence band, here is a conduction band. Once our electron gains some energy, actually the electron will start to possibly to jump across this region and reach to the conduction band. And once electron reach to the conduction band, it will become the conduction electrons here. So just like if we have the several kind of the incentive to trigger everyone start to move from the outside, then you can feel free to move there. So that's a same scenario that the valence band, just everyone sit here very nicely. But once there's some incentive, if you try to go outside, you can move freely. So this is same case. The electron here gets some energy, will be excited and start to move to conduction band and become the free conduction electron. And the difference between here, conduction band and valence band, that's what we call the band gap. And then band gap will highly determine the conductive electricity because the band gap smaller and larger also determine that whether these electrons are easily jump from here or there. So that's a very crucial material property. So we can also use this band gap, this energy band theory to understand some materials that we are very familiar with. For example, the insulator. As I already said, the insulator should be the material that the electron cannot be moved there. There's no conductivity in the electron. So that means the band gap here should be very, very large. That means in the end, there's no chance that the electron can jump across this band gap and reach the conduction band. That's why this becomes the insulator. And on the other side, the conductor. The conductor means that the electron can free to move there, and we don't need to apply additional energy here. So then you can see this is the band diagram. Then you will see the conduction band and valence band are overlap with each other, and there's no gap between. So therefore, that's why the electron can feel free to move between them. And then therefore in the between is our semiconductor. So that's just try to we learn some new series, but we also want to use this new concept in some material that we are familiar with and make sure that everything is consistent. Okay, so since we have the electron and hole, so the summary here is the electron is a negative charge particle, and then the holes are the positive charge vacancy that we call as a holes. And in the end, under external electric field, the electron can move, and then electron move toward the positive and hole move toward the negative, and that's in the end cause the electrical current. And this current is highly depends on the concentration or mobility of this electron and the hole. So that's a basic related to the electron and holes. Also, just one more thing what to say that related to band gap here. So we already say that the band gap is determined. It's very crucial. Also, it refers to their conductivity. So let's look at the distance between the flow. You can see that this is imagine that the electron is living in the low flow rate that we call the valence band. And to move freely, they need to jump to the upper floor. That's what we call the conduction band. And the distance between these four, that's what we call the band gap. So the smaller the distance, easier for the electron to jump. But the larger distance, that means difficult to jump. So that means, for example, let's look at the material that we are very familiar with. It's a diamond. So diamond sometimes can be considered semiconductor. Sometimes also can be considered as an insulator. And the reason why diamond, a little bit conductivity, but also it's very insulating, is because of the diamond has a huge band gap here, has a 6 electron volt. So the electrons in the bottom, it's very difficult to jump to the top. So this is not possible. It still can be possible happen. There are some people working on a diamond semiconductor, but you can still feel like it will be you need to provide this electron huge energy start to across this huge band gap here. Okay, so now we finish the materials, and the next one is we start to talk about the device. And before we talk about the device, there's a crucial one, what we call the junction. So the junction is a boundary between the different material. Just like that, if you try to drive from the paved road to the dirty path, then you will got a feeling in the between this paved road and the dirty path. Just exactly in the middle, you will feel like there's a slightly difference here. So this also will cause all the electrons, all phases difference. So that's why we need to study this, the junction. So junction will affect electron movement, current flow, and then also they are very essential for the device function and controls here. A lot of the semiconductor device, the property for device is mainly dominated by their junction characteristic. For example, the diodes, the transistor, and the memory here. And there are 4 important different type of junctions that in the old semiconductor, which we will start to talk about. The first one is metal semiconductor. So we try to put the semiconductor on top of semiconductor, we put a piece of metal, and we are curious what would be the transport characteristic between the metal and semiconductor, because you know this is 2 different materials, so it must be something happen in between. Another one is p-n junction, where we have said in the beginning that we put the p-type semiconductor on top of n-type semiconductor, and then we are curious that in the middle what happened. And we have this hetero junction, which means that we put the 2 completely different semiconductors together, and we have this MOS. This MOS structure is the heart of MOSFET, so which is very important. And why we call it MOS? Because of the full name is called the metal oxide semiconductor, and the abbreviation just use the first name, first word for each term. That's what we call the MOS structure. So we will talk about this. So the first one, metal semiconductor junction. So the metal semiconductor junction, just like the contact point between a plug and then also an outlet. Here, the metal supply electrons and semiconductor either receive or block them.
So this type of a junction determine whether can pass through the semiconductor smoothly or not. So this is a schematic for the metal and semiconductor junction. So as I say, we have a piece of the semiconductor. And on top of semiconductor, we put another metal, and then in this region, this is what we call the metal semiconductor junction. And of course, the figure A here is a schematic, but what is actually the real structure happening in our device is here. This is the one we will talk about later. This is our transistor called the MOSFET. But if you try to look at this, sorry, I think this drawings might not be accurate. So in anyhow, this is a metal. This is metal. Imagine this is a metal. So the metal and semiconductor is exactly happening in this region. Right? So this is metal and this is semiconductor. So this junction is metal semiconductor junction. The bottom is a semiconductor. And also we have a SAM here. Metal semiconductor junction, and also, sorry, this should be the metal here. This is all the metal. So now we have the metal semiconductor junction here, here, and also here. This is a structure of what we call the gallium nitride hand, which is very important for the energy and the high frequency application. So that's already widely used in some of the communication. So in the gallium nitride hand, this is kind of, the T here is still the same. The T here is always means the transistor. This is always means a transistor. So it's a one particular transistor called the gallium nitride hand. And we can see in this device structure, this all has a metal semiconductor junction. That's why this is crucial. But in here, we won't go detail what's actually the physics and then electrical characteristic for the metal semiconductor. Just a brief introduction that this is everywhere we have this. And another one is a PN junction, where we have already brief talk that the PN junction is a main block for our diode. So it's just actually a piece of the N-type semiconductor. And we put the N and P together, and then in between here, this is our PN junctions here, and this is the heart for the diode and then the solar panels here. And then imagine that this is N-type semiconductor, and what's the basic definition for N-type semiconductor? It's a piece of material full of electron. So that means we have lots of electron here, right? And then we have the P-type semiconductor. What does mean the P-type semiconductor? That means that we have this is a piece of a material that we have the holes, lots of the positive charge here. So right, so this is that's how we expand for N and P. And then imagine that if you put these two materials together, the first mechanism will happen. It's that following the very basic chemistry diffusion, that everything will try to diffuse from a high concentration to a low concentration, right? So this is a region where we have lots of electrons. So that's a high concentration of electron. This is a region that we don't have any electrons. So therefore, we can imagine that the electron will try to diffuse to the left. And also, the holes will try to diffuse to the right. Right? Because of this is a region has a lot of the positive charge, but this is a region that we don't have any positive holes here. So that's why we will have a diffusion to the right here. So that's a basic mechanism that in the PN junction we should expect we have electron diffusion and hole diffusion. But if there's only the diffusion happening, then after a certain moment, in the end, this material becomes the same concentration everywhere, because the electron will diffuse to the right, and then in the end become the equilibrium in the same electron here, same electron here. And we have a hole in the here, and then we'll diffuse to the right, and we'll have the same hole here, same hole here. So in the end, it will become the same concentration, but it's likely not could be possible because we won't see this. So that means we still have another mechanism that will cause PN junctions different. So we will talk about this later. And the third one is a very important one that we call the junction between the different semiconductor material. That's we call the heterojunction. So basically, we just piece of a semiconductor be one material, another material, and then put together, and then we can have actually create a very amazing electronic properties. For example, we put a gallium nitride on top of gallium nitride, just like this one, gallium nitride on top of gallium nitride, one kind of gallium nitride on top of another gallium nitride, and then that can create a different electronic properties. For example, very high speed electron transport. So this is just a two case. This is a gallium nitride LED that we use our daily life nowadays. So we cannot live without LED. So this is a structure for LED here, and this is Professor Amano, who actually invented, has a great contribution for the gallium nitride LED, and then he was awarded the Nobel Prize in the physics in the past, and because of thanks for his contribution for the gallium nitride LED. And this is a gallium nitride hand, also very important transistor here. And this is mainly contribution from the Professor Mishra from the UCSB. And then he has been working the gallium nitride hand for the last several decades here. And then if you use gallium nitride product, for example, gallium nitride charger or gallium nitride communication system, actually it's all based on his decades involvement in the gallium nitride hand contributions. Also, another one is the MOS structure that we have for the metal oxide semiconductor. So as I say, this is MOSFET. And then in the middle of this region is what we call the MOS structure, because we have, this is metal, and then the SiO2 is what we call the oxide. And then we have a semiconductor. So in this case, we just call this as a MOS, which is exactly structured like here, right? So this is the foundation of the transistor, which can be used switching the current on and off, and then we will also talk about this a little bit later. So let's just pick up the two most important ones. One is the PN junction, and one is the MOSFET, and just look at some more details. So as I say, PN junction is formed by using P-type and N-type semiconductor, and P-type has many holes here, and then N-type has many electrons here. So the first things can be expected happen is that the electron can move from N and P. That's because of diffusion. The holes can move from P and N. That's because of diffusion. So that's due to the diffusion series, just like you have hot water will prefer to diffuse to the cold region. So it's a very common, very simple ideas. But actually, we will not only have a diffusion inside the PN, we have something more cooler, which is that we have actually internal to induce certain of electric field. So when the electron move from N and P, actually we will have some positive ions left, which is here. So right, you have an electron move from right to the left, and then you have some positive charge ions leave here. And also in the meantime, you have a holes move from P and N, then you will have some negative ions left at this region, right? So actually this positive and negative charge here will create a region that we call as a depletion region. So the right side will become the positive charge, and then the left side becomes the negative charge. And then because we have this positive charge here, negative charge here, so in the end they will induce as a natural electric field inside. That's what we call the built-in electric field, or we call the built-in potential. Just like there's a tiny battery inside this junction. So therefore you will have this electric field here, naturally formed here, immediately after the P and N put with each other here. And this electric field will stop, prevent the diffusion of electron holes, just show me here. So you can see we have the electric field here. Original, we have the diffusion. Diffusion will try to move to the right, but we have the E field will stop the holes. We have the electron diffusion here, but we have the electric field will stop the diffusion. So in the end, this becomes the balance, becomes the equilibrium case. So that means this built-in electric field will help us to stabilize the junction. And then this case, normally we will further use a certain band diagram where we follow the concept of the band energy, the conduction balance band, to understand this phenomenon. But in here, I won't talk too much detail because it's way too complicated that I think everyone here still not fall asleep yet. It's already kind of amazing. So yes, let's just keep it in the last 20 minutes. Okay, so then we will have the, you can imagine that this is a certain kind of the band diagram help us to understand the phenomenon. And then once we have a P and N, so this is a region we have lots of electrons. And because of this built-in potential here, we will create the built-in potential, and this region, this is built-in potential here. And this built-in potential will try to stop our electron flows. You can imagine this is kind of like a step. It's like a small mountain. So then the electron cannot cross this small mountain. So then you will stop the electron diffuse. At the meantime, you have a holes here. So also the hole will face a small mountains here. So then your hole cannot be flow here. So this step is what we call as a built-in potential will, like a natural barrier wall, will block electron holes. So that's why that in the end you put the P and N together, but in the end you never had become the one material that the concentration is always the same. We still have P and N because of this the built-in potential create this the natural wall to block the electron and diffusion. So then we move a little bit further, but because I want to touch the part of the critical thing for the semiconductor, for the electrical engineering, that in the end we're always interested in the electrical results here. So the left-hand side is a condition under the forward bias. So what does mean the forward bias? It means that as being the electrical engineering or semiconductor engineering, the goal in the end is we are interested in look at the current versus the voltage characteristic. No matter what kind of material property, what kind of physics, in the end we hope use this knowledge to understand the current voltage characteristic. So in the left-hand side is what we call the forward bias. The forward bias means that this is a region we start to increase the bias here. So when we increase the bias, we can clearly see the barrier here is reduced. Once the barrier is reduced, suggests that our electrons finally can flow to the left. Our holes finally can flow to the right. And then, in this case, once we have electron and holes can be flow, we can expect that once we increase the bias, we start to have a current. We start to have a current increase here, right? So that's under the forward bias. The same if we try to apply under the reverse bias, which is we try to increase this bias in this region, which is here, reverse bias. This is reverse bias. This is reverse bias here. Then our barrier is increased. A barrier increase, that means likely you won't have electron flow. Our hole cannot flow. So therefore, we can expect once we operate this device in the reverse bias, we will have the flat. We don't have any current. So then we won't have any current here. So this will be the under the reverse bias. So just like say here, almost no current, like the blocking rod. So just this is an example. That's why we call this PN as a PN diode, because in the end, it becomes a one-way conducting. It can be only conducted one direction, but cannot be conducted in another direction. That's what we call as a PN diode here. So that's a just this is example to show that in the end, our goal is try to understand the electrical characteristic, which is most important is the current versus voltage. So here's a summary, just a quickly go through. Under forward bias, we have a current flow. Under reverse bias, there's almost no current flow. And then I believe that the slide is very detailed written. So if you want to understand more, you can try to look at in details. So the next one, I want to move for the MOSFET here. So that, as I already said, this is not our first time to mention MOSFET. So probably you already get some rough understanding. So MOSFET is a full name is a metal oxide semiconductor field effect transistor, and we take the first letter for each one that we call as a MOSFET. And this is a transistor like an electronic switch can be controlled by the voltage, just like the FOSI, but now it can control the electron flow or not. And then MOSFET has been widely used in computer, smartphone, power system, car. Is a key blocking for the modern electronics. And if you look at the MOSFET, actually there's several critical regions we just want to spend a little bit of time to discuss. The one is what we call the gate. Is here. We have the source is here. So the gate is just like the switch. Then we can apply the voltage, and then once we have voltage, we can have the current flow. And source is where electrons begin journey, and the drain is here. Is where electron exit the device. So then the typical operation is that we will first apply the gate bias here. Once we apply gate bias, as I already said, that the party bias will attract the electrons here. So you will start to foresee the electron might be able to accumulate. And because of a silicon dioxide is an insulator here, so ideally the electrons cannot move toward the top because this is insulator. But that's ideally. In reality, it's not. But that's just assumed in the ideal case. So electron cannot move toward the top. Electron can be only stay here. But right now we apply the positive drain bias here. So the electron cannot move top, but it will be moved to the right here. So electron will from this region. That's why we call it a source. This is source. This is origin source region. Origin region for the providing the source, the electron. So electron will start to move from here to here. In the end, become our drain current here. And then so imagine, as I say, the critical is our electrical result, which is in here we are interested in for the drain current versus a gate bias. In most of the time, we put it as a source grounded to simplify the case here. So we are interested in the characteristic of a gate bias versus a drain current here. And then based on what we have been explained, the operation mechanism, first, we start to increase our gate bias, and until a certain moment, we have enough electrons enough electrons here. So then we can start to see the current is increased. like this way. So that's a very important and it's basic, but it's very important characteristic. That's what we call the IDVG characteristic. So if you can under the operation for the IDVG, then basically you can understand everything related to the MOSFET. And some more details here, just quickly go through. We have a P-type substrate. That's usually we have some base material and put the N plus region. The plus means a highly doped concentration. And then that's easy for the electron enter and exist. And sometimes we have this what we call the body, which is a baseline voltage as a reference here. So here is a P-type substrate. We have a plus here. Plus means that we have very highly doped concentration. Sometimes we even have a plus, so that means even higher doped concentration. Okay, so as I already said, the MOS structure is a core part for our MOSFET here. So then for sure that before we understand the MOSFET, normally we'll spend a little bit of time to talk about the MOS capacitance. In here, we won't talk too much detail. Just want to share that this should be the very basic equation that probably, at least in Taiwan, I think the high school students should already know this. So this is basic, the charge is equal to the capacitance times the voltage here. So therefore, if we apply large voltage, we should get more charges here. So therefore, we can consider this is higher gate voltage, more charge. So the MOS structure just like an electronic gate. Then you can start to modulate our channel conductivity. So you have apply more voltage, then your bottom material semiconductor become conductions. If you know voltage, that becomes the things, the material that can block a current. So that's why the MOS structure is the core part for the MOSFET. And regard for the MOSFET, the basic operation here, I think I have already mentioned previously, but in here there's a lot of text here, so I won't go to detail. I just quickly explain once. If you are interested, you can find more materials afterwards, or you can check with me. So in the beginning, as I say, what we're interested in is a drain current versus a gate here. But so this is condition of gate bias. We start to increase our gate bias a small, but still below as a one criteria that we call the threshold voltage here. So this is a criteria that we call the VT here. And in this moment, that because of there's no electrons here, so then we can expect that our current is equal to 0 at this moment. So the ID is equal to 0, and this is our criteria that we call the threshold VT here. And then afterwards, we start to increase more and more our bias here. So now we apply the bias VG larger than VT here. So as already said, that at this moment we start to have an electron, right, accumulate under the channel. But at the meantime, we have a VDS here. So therefore, we can expect that the positive bias in the drain side of electron can be moved forward to the positive bias and then become the current here. So then back to our exercise to complete our IV curve here. We have an ID, VG, and then we have been shown that below VTH, there's no current. But now, beyond VTH, we can see there's a current can flow to the drain side. That's why the curve will be look like here. And then this will be the nice to make a comment that this is exactly the region where we call the ion. As you still remember in the beginning, we say our goal is to increase ion, but also this is exactly the region for the ion. So we want to make the off current as smaller as possible, but on current as higher as possible. Now you probably start to get some idea where is ion, where is IO. It's from the MOSFET operation characteristic. So the rest of all you can read by the text letter is very easy to understand. Okay, so that's another little bit more that how actually from the planar to the powerful chips. Is that in the beginning we already mentioned that this is a MOSFET, but now we are moving in the age of the FinFET, and then we have the description here. So the planar transistor like MOSFET, just like a one-story house, we can only have a one gate to control. But in the case with a FinFET here, it's like the 3D house. We have the multiple floors, and then we have the gate can control not only the front side but also the side walls here. So that's become the high performance, low power. So that's very important for nowadays technology so far. And then normally when we try to finish the device fabrication, we will be interested to look at how the device in reality. So this is what we usually do for the electron microscope. So in the case of electron microscope, we can really see this is our film. This is our film. This is exactly the same like this region. So this is a real FinFET structure under electron microscope. So for the MOSFET, we have another very important characteristic, but in here I won't talk to again because that's a little bit very complicated. So just let you know that we're also interested for ID, VD characteristic. We have a linear and saturation, and if you are interested in, you can look at later. So finally, just another 5 minutes is enough that I will talk about the semiconductor fabrication. So in this class, I think the purpose is not to talk about the fabrication, and I want to actually to focus more on the materials and device, and also give you some kind of a feeling that actually the semiconductor is very important also for the device design, not only for device fabrication. Device design is very crucial because in the end, we need to understand device physics, and then we create a better device design to improve our current performance. And then for sure, once we have a device design, the next phase is how do we fabricate? How do we really produce this semiconductor? So semiconductor are actually the brain of the electronics, as you can know. And then the process need to be in the scale of ultra precise, just like we build down a lot of the high tech, but it's a tiny house here. And then all they have to be done in the clean room because of we need to avoid lots of the contamination, avoid lots of the dust issues. So we need to all finish this in the clean room. So the step one is we have a wafer fabrication. So we start with the ultra pure silicon, and then we will start to grow a large silicon crystal ingot here, and then we will start to slice into the wafer, show me here. So we will slice our crystal ingot to the wafer, show me here. So that's how we get it as a starting material as a silicon wafers. And the next one is that we will start have this oxidation process, as you already know. For the MOS transistor MOSFET, silicon dioxide is crucial, so we need to find a way to grow as a silicon dioxide, which is here one. This is act as a protecting. This is SiO2 here. That's you may need to act as protecting for the bottom silicon materials here. And then we have very advanced photolithography process. Just imagine this is like the photo that you take a picture, but now we want to take picture in the extremely small scale. So like taking a photograph, the light is used to print the circuit patterns on the one wafer. So we have this kind of camera that we call the photolithography process, and then we will print our circuit in the wafer here. So use light to project certain patterns onto one wafer, just like taking the high precision photos here. And then this is a very critical step, so that's why we need to have EUV, because we want to make it an extremely small circuit, so we need to have very precise and then very small line width, this kind of a photolithography process. And the next one is that we will deposit certain material. Just when try to think about it, like we try to build the walls or floors. So we will put some conductive or insulating material. So we will step by step to staking our semiconductor chip, just like the building the house. It's the same concept. And then we'll do some etching. It's like we try to etch away certain region that we don't want. Just like as a similar, we build a house. Some place we want to have the empty room. Some place we want to have the living room. So we need to etch away some place we don't want. So that's what we call the etching. So we use a chemical solution or plasma to remove the unwanted materials here, just like shown here. So in this case, we leave this pattern that we want and we etch away this region that we don't want. That's how we do the etching in the end to form the circuit pattern. And also, as I say, it's pretty important that we need to make sure we can dope. We want to change the conductivity to even more highly doping or less doping. So therefore, we need to put some additional impurity that we call the dopants here to make this as a P-type or N-type, and this can make sure that our specific area can have a different electrical property, and that make our device and circuit and system functionable. And the last step is we will do the testing and packaging here. So each chip is tested to ensure that it works correctly, and then also we will package our semiconductor chip, and then in the end become the processor. So you can see that this is, if you open your semiconductor, if you open your smartphone, you're likely to see the many of the packaging chips here. So that's lots of step here. So last part, this is a short takeaway. So that we spent the last 2 hours together to look at overview again. What is a semiconductor? So semiconductor is just a material that between the conductor and insulator is like the electronic switch. Then we can turn on, turn off the electronic current by our needs here. And then the transistor for sure is very important for semiconductor, especially the MOSFET. Of course, the other bipolar, we have many gang-hand. They are all very important in the different kind of application. And one thing you should always MOSFET is a key. And one thing you should always know is about Moore's law. Is the behind kind of the behind law that try to drive our semiconductor progress, and then this means the density will be double every 2 years. And then what we have been done in the past for the decade for the innovation is from the planar to 3D, and we have a FinFET, Gate-All-Around, EUV, and lots of new materials make our chip better and better. And also to look at the future nowadays, we have a 3 nanometer to beyond 1.5 nanometer and being further and further. So we still need every of you to be involved in the semiconductor wars here. So I believe that this is a great opportunity, not only for us, but also for you guys. You guys will be the future. If you are interested for the semiconductor, I believe you will be the future star in this field. This field can be the one that the not only to change the technology, but there is also the technology that can reshape the world. And then if you're involved in this field, you will be the one who can reshape the world. Okay, so great. So this is just some reference. So the first one reference is the semiconductor physics device. As I say, this is courses that I lecture in the NYCU every semester. And if you are interested in, you can look up, to be honest, you look at my name, you will find actually I upload all my lecture video in the YouTube. So actually you can, if you are interested in a particular concept, you can look at this online material, online lecture recorded videos. So that's all. So thank you for the attention. And then I hope that you got some interesting understanding for semiconductor, and then probably it's also combined with some of you, I hope you had a nice sleep as well. Okay, thank you very much.